So we will continue the remaining part of chapter 3. We have seen together last time that for fluids, an important characteristic is the viscosity, and the viscosity will relate the shear stress to the shear rate. Okay. Now we will introduce several possible behavior of fluids. You will see fluids having constant viscosity. Of course, when we say constant viscosity, is it for a certain temperature? Okay, because viscosity is always will always vary with temperature. Because imagine that you have a solid and you heat it. As you heat, it will go from solid to liquid. So it will go from infinite viscosity when it is at the solid state to reduced viscosity when it becomes a fluid. Okay, but if we do the analysis at constant temperature, then the viscosity can change with the shear rate or can be constant. So in case for a certain temperature, in case the viscosity is constant with the shear rate, this is called the behavior of a Newtonian fluid. So as you can see here, this line at the middle, which is a straight line, is the behavior of a Newtonian fluid, where the viscosity represents the slope of the curve and it's a constant slope, since by definition the viscosity is the slope of the stress function of shear rate. Okay. Now, what other behaviors we can face? We have the ideal Bingham plastic, which is, if you want, it's not defined as a solid and it's not defined as a fluid because it can behave as a solid for certain stresses below a certain yield stress, and above the yield stress it will act as a fluid, because as you can see here, for example, with between 0 and nearly 72 for the stress, we don't have any shear rate. This means that we don't have deformation. So for stresses between 0 and this limit, we have the behavior of a solid. However, when we exceed this yield strength value, then we begin to see a deformation, okay, and we see a shear rate, and then we can see that for this part, for stresses higher than this point, it will behave as a fluid having a certain viscosity, okay. So this is called the ideal Bingham plastic, which will change behavior depending on the value of the stress. Now, for non-Newtonian fluids, we have several possible behaviors. Okay, we can have increase of viscosity with shear rate, or we can have decrease of viscosity with shear rate. For example, if we consider shear thinning fluids, okay, this is the case of shear thinning fluids here. As you can see, the viscosity will be reduced with the shear rate because the viscosity represents the slope. And if you observe here the slope is decreasing as you are increasing the shear rate. Okay, so in shear thinning fluids, the viscosity decreases with increasing shear rate. Therefore, the harder the fluid is sheared, the less its viscosity. And we can have as example for this latex paint. Okay, because look, for example, if you want to paint a wall, latex paint does not drip from the brush because the shear rate is small and the viscosity is large. But when you flow it smoothly onto the wall, it will create a thin layer of paint because between the wall and the brush, because of the large shear rate between them. Okay, so for a latex paint, when it is before putting it on the wall, you can see it's viscous. But once you begin to paint on your wall, what will happen is that the high shear rate created between the brush and the wall will reduce its viscosity. Okay, so this is an example of shear thinning example. Now, another behavior of non-Newtonian fluids, okay, is the shear thickening fluids. So in this case, it is the opposite behavior. So what will happen is that the viscosity will increase with the shear rate. And as you can see here, you can see it from the variation of the slope. So the slope is increasing as you increase the shear rate. Okay. So this is the second type of behavior, which is shear thickening. And common examples of this type of fluid include, for example, the mixture of water and sand. If you mix water and sand, at the beginning it seems that you have a low viscosity, but when you mix them with a high rate, you will see that the viscosity of the mixture will increase. Okay, and for Bingham plastic, can you give me an example for the one who will behave as a solid for small stresses and fluid for high stresses? Who can give me an example? Think about the toothpaste. Okay, you know the toothpaste looks as rigid, but when you squeeze it, it will become as a fluid. And also you have the mayonnaise. Okay, so for example, mayonnaise can sit in a pile on a slice of bread, but if the shear stress is, as long as the shear stress is less than the yield stress, but if you put on it a knife, okay, and it can flow smoothly when the knife will exert on it a certain stress above the yield stress. Okay, so these are examples of Bingham plastic. So this is what we should know about the different behaviors of fluids. Now, another important behavior is the viscoelastic behavior. Viscoelasticity is a property that determines the strain that the material will experience when subjected to combination of stress and temperature over time. So here we will take into account the time effect when we talk about viscoelasticity. So it is a combination of viscosity and elasticity. To understand more what we mean by this, let us here compare the behavior of elastic versus viscoelastic behavior. In the first graph, in graph A, you can see the response of an elastic material. What will happen is that I will instantaneously apply a certain stress. I will maintain the stress constant for a certain period of time, and I will then remove the stress. And I will look at the response of my material. I will observe the strain. I can see that the material will spontaneously respond to the stress. So when I apply instantaneous stress, I have instantaneous increase in strain. Then when I keep, if you want, constant stress, the strain will remain constant. And finally, when I remove the stress, also the strain will instantaneously go to zero. So this is the response of an elastic material. On the other hand, for the case of viscoelastic material, it's quite different. So the first difference is that, of course, first, once I put a stress, I will have first a sudden elevation of strain. But if I maintain the stress constant, then the strain will increase gradually function of time. Okay, so the response is not, if you want, instantaneous, it will take a certain time. And then when I remove my load, when I remove my stress, I will not have instantaneous, if you want, I will not go instantaneously to the initial state. I will go back to the initial state, but with a certain time. Okay, so I will have this curve like this, and it will take me time to go back to the initial state. So this is the viscoelastic behavior. So I can deduce that the viscoelastic behavior will not have instantaneous response to stress. We are done with chapter 3. As I told you, I will post for you a formula sheet for all formulas included in the chapter. And the formula sheet also will include other formulas that will be involved in the exam. But you will see that we have covered, chapter 3 will cover the majority of equations. So let me go over the formula sheet with you. So this is the formula sheet you are responsible for. You should know the different relations. So first, you have the definitions of engineering strain, engineering stress, ductility measurement. how to calculate the tensile strength at the maximum force over A0. What is the definition of true stress? What is the definition of true strain? And what I want, and here you have the elastic region, you have sigma equal E epsilon. Now, what I want you to do is to try to demonstrate these relations, okay? You have relations between true stress and engineering stress, and also true strain and engineering strain. These are the formulas, but we will demonstrate them together, okay, in problems. So try to think about it now during the weekend, and I will post for you also several problems that you will try to start with. Now, as I mentioned for you, for the Brinell hardness, you have a formula. If you remember yesterday, we have seen the Brinell hardness test, which consists on a sphere that I put on a specimen. Okay, let me go back if you want to the slide. So here, this is the Brinell hardness test. We have a way to calculate the hardness function of these parameters, which are the force that is applied on the sphere, the diameter of the ball, which I put on the specimen, and the shape of indentation, the resulting diameter of indentation dr. So we can see here that the Brinell hardness can be calculated function of these parameters. Just please pay attention for units. Okay, so you have particular units in this formula. In this formula, the force F is not in a Newton, it's in kilogram. It corresponds to the mass of the ball you are putting on the specimen. Okay, so please pay attention. A lot of students do this mistake. They replace F by the force, not by the mass. This will give you a wrong result. Okay, so the force is instantaneous, is the load in mass, if you want. dB and is the diameter of the ball, and it's in millimeter, while di is the diameter of indentation and also is in millimeter. So just pay attention for units. Okay. Also, we have developed, in general, the majority of materials that were tested in hardness were metals. And we have come up with an empirical relationship for steel that will give you the tensile strength function of the hardness. So this is also an empirical relation that gives the tensile strength if I know the hardness, okay? And in this case, the tensile strength we obtain will be in megapascal. So here the unit will be in megapascal. We will do application on these formulas in the problems together, okay? So this is in megapascal. Now, other formulas that are important, we have seen already together that we can relate shear properties to stress properties. So you have the relation between shear modulus and modulus of elasticity. G is approximately 0.4 E for most materials. And also the shear strength can be estimated function of the tensile strength from the following relation. Concerning shear viscosity, you have that the shear stress is the viscosity times the shear rate. Okay, so this is the formulas involved for shear viscosity. And the remaining part I will introduce it for you in next chapter. So the remaining formulas are not for chapter 3, are for the other chapters, which are included in the exam. Okay, so but as you can see, the majority of formulas are in this chapter, chapter 6. So now we are done with chapter 3. Okay, I will post for you problems to start doing chapter 3, and we will correct them together after. Now, if you want, we will start with the chapter 6. Okay, and for chapter 6, I have prepared for you several YouTube links that are very interesting, to see how because this chapter is more experimental, as you will see. Okay, so I prepared several YouTube links for you. If you can try to go over them during the weekend to be familiar with the chapter. Okay, so let us. I will close this session and open a new one to start with chapter 6. Okay.